anything incriminating. Away we go. I'm going to share my screen. This is just a Chrome browser, so no trickery. This is very, very simple. So when you go to science.nasa.gov/eyes, you will come to my homepage. And this is where you can access every single app, visualization app that we have. You can also, it used to be called eyes.nasa.gov, and that will also work. So first thing you see is you'll see a bar on top here. And here are the applications, all of the applications that you can use for free. And I'll get into what you can do perhaps in the library because there's multiple options. But this is free to the world. It's real-time 3D updated constantly. You can see some highlights here on the video reel. So all of that is in the app. None of that is rendered. That is all in browser. So in any browser, your cell phone, any mobile, any Linux, any Mac, PC, whatever has internet and a web browser, you can use Eyes. So just little cool things you can do in Eyes. Description of the apps, but I'm just going to get into the apps because there's a lot to show. So I will start with the flagship, Eyes on the Solar System. So this was created about 10 years ago, and it was a Unity-based video game that you had to download and install. But now, here it is, browser-based. It is real-time. I'm going to go full screen. So you're looking at a very easily interactable 3D simulation of the entire solar system. And you really want context. There's your context. So you can zoom out to the Milky Way. And let's go back into our sun. Every star is accurate. Tycho 2 catalog here for the stars, brightness, etc. And as we go into the solar system, you can track 163 missions. And that is all available by search or by the menu. So we open up the nice simple menu and you have 162 spacecraft. So if we click on that, every single mission you see here, you can watch from start to finish. So for example, Voyager. If we click on Voyager 1, it's still alive. So when you go to a spacecraft, this is its current position. That is its actual size. That is a model made from the CAD, the engineering model. And you can actually fast forward or rewind time. So if you're really impatient, you have 100 years to play with. There's also an events timeline that you can use. It'll give you all the major events of Voyager. Like you can jump straight to Voyager 1 at Saturn, for example. This is like a bookmark. So now, as you see, we're back in November of 1980, and you can just type in whatever time you want as well. But this is the classic first Titan flyby, going at 1 hour per second. And at any time, you can just stop time like this, and you can drag time forward 21 hours per second if you're really impatient. That's the end of the event. So if I go back to Voyager, now we're just free flying in 1980. So here we are, 1980, paused. I can start again. This is real time. So we have 100 years simulated exactly because we use the real engineering data. We use what are called spice kernels, which give the actual trajectory of all of these spacecraft. And every position of every moon at this time is accurate. And you can really go fast if you want to. So this might skip online, but that's 1 month per second. And you can actually go years per second. So this is 2 years per second. And you can see Voyager heading out north to leave the heliosphere. Eventually it will leave it. Let's turn on the heliosphere. You've probably never seen this before, but let's go ahead and get out. So that's 3 years per second. Voyager 1 leaves the heliosphere right about here. And now we're at 2030. So that's the end of Voyager's data, but that's not the end of the solar system's data. So there's a lot of fun little tools you can do. So on the left, you have an information panel and a little description, a longer description. And then there's a storytelling element right here. You can click on this. It's interactive 3D storytelling. So you can see the trajectory, and you scroll on the left, see the action on the right, and you can interact with the 3D. And that's the real movie of the first movie of Jupiter we ever had. It's called the Blue Movie, where we saw the red spot moving around. This blew people's minds back in '79. We found the volcanic explosions on Io. These are all the real pictures from the event, including this cool GIF of Io rotating and having volcanoes. Anyway, you scroll through and you can see the whole mission just like that. But I'm going to close that. There's also a sharing button you can do. Share with the world. So when you go to Solar System, you're pretty much can do whatever you want. So if I go into menu again, you can see 302 planets and moons, including some of the most recently found ones. So one thing you've probably never seen is every single minor moon. By the way, there's the full shape of the heliosphere, which is pretty cool. It's like a blue whale, and it's many, many AUs long, many astronomical units long, and that is our shield of our whole solar system visualized. So that's where our solar wind protects us from the outer wind, which is pushing against it, which creates this long, oblong teardrop. And then we are heading to a certain constellation. You can actually turn on the constellations here. You can kind of see the direction we, as a whole, are going in our journey. You can also ruin the constellations by zooming out. They are location dependent, but yeah, so that's pretty cool. So let me go back into Voyager. Okay, so let me show you something you've probably never seen is every single minor moon. You turn off the constellations. You can turn off layers here. So if you don't want trails, orbits, labels, or icons, that's what you're left with. So not very exciting. So we want to turn those back on. So let me show you, for example, Jupiter. So here's Jupiter. We do have a mission there right now, Juno, which you can see here, which we can look at. But this is Jupiter, and we're all familiar with the big four, but there's also many, many minor moons. So if we go down here and turn on minor moons, it'll add 91 more moons, which you've probably never seen visualized. So there they are, quite complex, the ball of yarn. They move a little slowly, so you have to really go fast to see them move. That's 2 months per second. You go back to live. So the goal with eyes is to show things visually to inspire wonder, get people to invest in their solar system. Here's some tools right here. We can pull up the distance tool. We can see how close it is to its orbiter. Just search for Juno, and it'll tell you the distance, just like that. So it's 3.26 million miles away. I can fast forward. You can see Juno's orbit, which is very oblong because it's trying to stay away from the radiation belts of Jupiter. So if I fast forward, you can see how long the orbit takes. So kind of a cool little tool to show people how things work. We also have compare size for everything. Go back to live, it's spinning a little fast. So compare size, we have a left to right comparison. You can just kind of scroll through planets, and you can, the sun dominates Jupiter. And our moon, much smaller. So little things like that. You can also follow a target. So if we want to follow a moon like Europa, you can just search for it, do this. And now as we fast forward, we have the camera showing Europa with Jupiter. So that's kind of cool. And anything you see here, you can just take a screen recording. Like you can make it look like this. You can turn this off. You can even customize more than that. But you can just capture this with QuickTime or with, if you're on a PC, with OBS Studio, a free tool. And this is just a little video you can make immediately. Bring back the panel. Go back to Jupiter. We're back. Time controls live. So also on the left here, we have kind of events. So we can see the entry, descent, and landing of Perseverance. We can go to Clipper launch, which just happened October 14th. Or you can see an upcoming cool event. This is like a little bookmark. So here's Parker Solar Probe getting closer to the sun than anything ever has, which is pretty incredible. On Christmas Eve, it will do another perihelion of its long orbit. So this is kind of a fun event for NASA. It's getting this close. Nothing's ever been that close before. So this is unprecedented. We're way inside Mercury's orbit, even. All right, let's zip over to Mars. We have a nice fleet at Mars. So you pull back, you can immediately see everything going on there. And down at the bottom of the panel, you can actually upgrade the textures. So let me turn on a global mosaic from Viking, which is still very, very good. And you can see really good detail on the surface of Mars. Here's an orbiter, Mars Reconnaissance Orbiter, that's been there since 2006. And it has a telescope here that can see 1 foot per pixel from orbit. So it can see the rovers on the ground, and it's still going. Turn that map back on again. This is where it is right now. If I hit live, so this is where it is. Above Mars, everything is accurate. You can find related missions down here. You can turn on and off the moons, the landers, the orbiters. You can also go above the sun. That's a little far. Let's go above Mars. The view changes. Now you can kind of follow MRO from top down or back to MRO. So there is a lot to do. There's a lot to do in this program. Another thing you can do is share this. So you can quickly go to the link of this thing, or you can actually do an embed. So if you're an educator, if you have a website, and you can put this on the library's website if you want, you can just pick something you like. So like if you do want to show Mars and you don't want anyone to search and you don't want the panel, you can just customize your embed. And let's say we don't want can't navigate away now. No external links. So this is, someone could walk up to a touch screen, or you can put this straight on your website. And here's the iframe code generated for you. So you put this in your web page and it'll open up a little 3D window showing this that people can interact with. You can copy the embed code here. So that's kind of like a self-service embedder for your website. That's kind of a fun feature. All right, there's so much to do here, it's unbelievable, but you can do a program at your library about certain discoveries. Like we go to Saturn, you can just show cool things like the real lighting of Saturn, natural light. The ring shadows, we're almost at equinox, so the ring shadows are pretty level, but it's really fun to fast forward and watch the shadows go. So over time, the ring shadows will move north, enter in the northern hemisphere, and it's something really cool to visualize. And this is all accurate data. This whole cycle takes 28 years or so, but it's all accurate. So we're at 2034. It will stop at 2049. That's the limit. But you can really go fast. You can go 2 years per second and watch it very fast. But we're going to run out of time right now. So that's a fun little visual. Let's go back to live. There's also missions connected with this, so you can see them here, the exploration missions. Like the Cassini mission is absolutely incredible. So the Cassini mission launched in '97, and here you see it launching from Earth. And it headed out to Saturn. And then eventually found geysers of ice crystals in space at this moon called Enceladus, which is insane. So this mission discovered that there is geysers. There are geysers from the South Pole of Enceladus spewing crystals into space 24/7. And we visualize that. So let me light it up for you so you can see. So there's fissures in the ice whereby it's spewing what we thought would be water. So we actually sent our mission into it to taste it. So in 2015, we actually sent the $2 billion spacecraft right through these particles. So we put out the spectrometer, we tasted it, and indeed, this is water. So it's 99% water and 1% organics, which was really mind-blowing, which means with energy, water, and organics, you can have life. So underneath this icy crust is a subsurface ocean that might have life.
Jason, actually, that's a question that people often have. When you say organics, could you just clarify that doesn't mean life itself? It means something different.
It does not. It means like ammonia that you have in your kitchen sink. It's methane, ammonia, something with carbon, a molecule with carbon. So we positively detected those by running right through those ice crystals. So we know for a fact there are organics underneath there. Organics can form over time with energy and water into life, to the best of our understanding. Now, these would be very, very, very small, not the Loch Ness Monster. These would be just tiny little amoebas or protozoa. But the point is, we might have life in 2 locations in our solar system already, besides us. That's why we're going to Europa, which has the same situation. Icy crust, subsurface ocean. Okay, I am going to leave Solar System. This is the flagship. It is embedded in various NASA sites for various missions because we do have 162. And let's go to another one. So we do have a lot. Let me show you Eyes on Asteroids, which is very fun. This actually tracks 35,000 near Earth objects in real time. So these are the asteroids that are quote unquote threatening us. These are the ones nearby Earth. There's a million asteroids, but this is the 35,000 closest to Earth based on a certain parameter. So we visualize them. So here we are. I'm going to fast forward. Here they are. Every little blue dot is accurate. That's exactly where it is. We've also sprinkled in some rock star asteroids and some rock star missions. So certain famous missions like Lucy, which is going out right now, Psyche, which launched, they're in here. Osiris Apex, which used to be Osiris Rex, is in there. And that is them in real time. So let's go back to live. A really fun thing you could just have up on display. And actually, let me talk about what you can do in your library. You can get a miniature computer. You could even get like a Strawberry Pi, but you can get like a mini Mac or a mini PC that is like the size smaller than a box of tissues. And you can set it up with a touch screen right in your library and have this going all day. And kids, adults can come up and use their finger and navigate. So everything I'm doing here, you can touch on screen. And there's ways to do that Amelia and I can help you with. There's special kiosk version as well, which you can set up. But all it takes is the touchscreen is actually the biggest investment. And then the computer is not, because we just need it to run a browser. But the fun feature is Asteroid Watch. So these are the next 5 asteroids threatening Earth right now. So you can see them in 3D. It actually helps clarify that they are not, in fact, that close. But that is where they are. They're reasonably close. You can actually click through them here one by one. And you can see how close they get. Let's change that to miles. Just click on it to go back and forth. So it only gets 1 million miles away. That's not very exciting. None of these are getting anywhere close. So I don't even pay attention unless they're within the moon's orbit. And you can see they're way off the moon and they all miss. And if you're impatient, you can just fast forward and see. Fast forward, you see where they go. This is typical. And the size, this kind of size is typical as well. They're pretty small. Well, that one's kind of big. But most of these will be burned up in the atmosphere anyway. And it's so rare. But it does happen. Sometimes we'll get one that we only find about 3 hours before it makes it into our atmosphere. But those are small and they usually burn up. Sometimes they do make it through. Like there was a huge one in Russia about 10 years ago, a little more than 10 years ago. And that one you can see all kinds of dash cam footage for, but we track every single one. My group made this in conjunction with the Planetary Defense Coordination Office at NASA. And their job is to track every single object that is coming within a distance of Earth. So coming up soon, we have a close approach of Apophis. And this is how close it gets in 2029. This one's very, very exciting because it's 1,000 feet across and it comes only 20,000 miles from Earth's surface. So that is absolutely inside some of our satellites. So it is going to miss Earth, but it's a very outstanding opportunity to find out more about it. We're actually going to send a spacecraft to hang out with it at this time. So that's pretty exciting. So again, it will not hit Earth, but if it did, that would be quite a lot of damage. This is very rare. So this close approach is like once every 100 years. And something big doesn't happen very often at all. So, dinosaurs got a big one 66 million years ago, and that's not very often. That's not something I would have anyone worry about. But even if an asteroid were to hit us, we can actually save the Earth, and we know how. There's a mission called DART, which you can search for here and go to. We tested the ability to alter the trajectory of an asteroid with this spacecraft. So here it is at launch, 2021. And a little bit later, a year later, it actually impacted this binary system. This binary system was innocent and not threatening us, but we're doing this as a test. So we actually slammed into it. We destroyed our spacecraft, destroyed the $160 million spacecraft to see if we could move the orbit of the little one around the big one. And we chose a binary because it's very easy to measure the change in its orbit when you have a binary. So it was a massive success. We found out we moved the orbit by 33 minutes. It actually goes around faster by 33 minutes because it lost mass when we smacked into it. So the point being, we now know we can alter the trajectory of an asteroid if we see it early enough and we just fling some hunks of metal at it. You don't even have to alter that much, just a little bit. And then if it was going to hit Earth, we just nudge it gently and it will miss Earth. So yes, we actually figured out how to save the world during just a couple years ago. So that's good. Okay, there's other things you can do here. You can run through the storytelling. Let me actually show you the definition of what's a near-Earth object. So a near-Earth object is anything that comes within 1.3 astronomical units of Earth. So around this white line, if your asteroid gets within this line around Earth's orbit, then we call you a near-Earth object. That's it. That's the definition. Now, we have another category, which is worse. Potentially hazardous object. And that is inside this inner tube. So if you are within about 5 million miles of Earth, we call you a potentially hazardous object in this like inner tube boundary. So you can see Apophis entering the boundary here in March of 2029, and it will get very close to Earth, the one I just showed you. So that's a potentially hazardous object. There's 2,400 of them. So we track all those as well. And of course, NASA tracks them all the time. So we keep a pretty good eye out. So that's Eyes on Asteroids. Always a fun thing to show. Let me show you Eyes on Earth. Eyes on Earth will show you all the latest data. How are the vital signs of Earth? What is going on with Earth? Is Earth healthy? How is climate change doing? We give you instant access to the latest data sets, such as you can see at the bottom. First, you're looking at yesterday's imagery of Earth. So if I zoom in, it was a pretty nice day yesterday in Southern California. That's real imagery from yesterday, globally. And every mission is in its proper position, just like other EYES products. And let's go into a mission that's very exciting, like the ISS. Let me go find the ISS. It's down here, South Pole. Just like the rest of EYES, anything you click, in you go. And there it is. So that's where it is right now. That's how fast it's going. And you can see the solar panels tilted to catch the sun. And those change over time, which is kind of cool. But even better than that, we can get the data on a little Netflix menu of data. So if I go to vital signs, here it is. Any one of these you click in your little Netflix menu, you can just visualize the data. So now I've clicked on air temperature, and this is temperature at the surface. And anywhere I click, it will tell me. Anywhere I click will tell me what is the temperature. How is Chicago? It's cold. So the blue line is actually freezing. And we map the whole globe. This is a 3-day average. But if I wanted to show a daily average, it's not very attractive. So this is today, but it's not done yet. The satellite here has to mow the lawn. So it's not done creating all the orbital passes needed to get the data. So we do a 3-day average, which is pretty close. So here, anywhere you click, you can see it's summer in the south. So South Africa will be really hot. Australia will be hot, the outback. And you can change the Celsius down here for the rest of the world. Every single pixel will tell you the data. And even better than that, you can go back in time. So let's say we want to watch winter. So we just pull up the month and date. We do January, just the whole month of this year, and you can see how winter is in North America. You can see the freezing line jumping around, which is probably something you've never seen before. So you can see the Rockies will sometimes freeze and unfreeze first, and then you can just go around the world. You can see that Siberia is not playing around. That is a lot of frozen territory. If I go here, wow, that's really cool. That is very, very cool. So that's temperature. We have everything else, and we may as well jump on the big one, carbon dioxide. So carbon dioxide is the basic, in a nutshell, the source of climate change and how we refer to climate change is based, we call it carbon. How much carbon is in the atmosphere? And that includes, we kind of commonly refer to that, or the carbon dioxide equivalents, to mean the greenhouse gases. But first of all, carbon dioxide is the big one. Everywhere I click, it's 423 parts per million globally. And that means if I take a box of air in the atmosphere, only 424 out of a million are carbon dioxide, which sounds like nothing. But the change in carbon dioxide is pretty rapid, just over 20 years. So here we are, 20 years ago, we were at 370 parts per million. So in 20 years, we burst through this scale. We're now at 424 globally. The reason that's a problem is we've never been in this situation before. We actually know how much carbon dioxide has been in our atmosphere for 800,000 years for a fact. Here's the historical carbon dioxide chart. So for 800,000 years, we never went over 300 parts per million. And human beings only started around here. So we've actually never been in the situation where we have 420 some parts per million. But what is the problem? The problem is carbon dioxide loves to absorb and prevent a certain wavelength of the sun's energy from returning to space. So every day the sun sends us energy and life, and it's primary in the visual, like green, red, orange, yellow, green, blue, indigo, violet, peaks at green. So carbon dioxide does not care about the predominant wavelength of the sun on the way in. The problem is when it hits the ground, the earth absorbs some of that energy for life and plants and food. And then it wants to radiate the extra energy to space after it's taken some of that energy. The problem is it reduces the wavelength, makes it weaker, and turns it into infrared. And that's the wavelength that carbon dioxide loves. So when carbon dioxide when the earth tries to cool off at night, for example, instead of radiating that extra energy to space, it's trapped. Carbon dioxide, methane, nitrous oxide, and even water vapor will trap that energy and send it back into the environment rather than letting it escape. So you can see over 800,000 years, it always went up and down. There's variations, there's ice ages, there's volcanoes, and that's normal. But the Industrial Revolution, you can clearly see, has made it go exponential. So oil gives us a lot of our society, but there's a cost to it. And the cost is too much energy in the atmosphere. So the weather will become more crazy, as everyone knows. The weather you grew up with as a child is gone. So we've never been in the situation. A 500-year flood becomes a 50-year flood. A 50-year flood becomes a 5-year flood. The problem is there's just too much energy pumping around. So a hurricane has so much more power now. Hurricane has hotter sea surface temperatures to draw from. It has just generally more energy available, so it slows down and it does more damage. Weather events become more extreme. And this is something we see every day. So this is not a surprise to anyone. I think everyone knows that this is something we have to deal with. But we here at NASA, we just collect the facts and we hand them over. So the data is public to the world, including some other interesting vital signs like sea level, which we go back a long way with. We go back 30 years on sea level. Carbon monoxide, which is fire. You can immediately see the Amazon is burning, and it always does this in the fall. So that's slash and burn agriculture that we can pretty much see clearly. So it's particularly bad in the early fall. So if I go to September, and go till now, we'll just kind of see it. So there's September. This is parts per billion with a B, billion. So it's not as catastrophic as it looks, but that is an indicator of fire. And that's blowing the carbon monoxide molecules all over the earth. And some of that can turn into CO2, but mostly it's just toxic in high quantities. You have an alarm in your house that goes off at 300 parts per million, actually more like 100. And this is parts per billion. But it's quite clear fires in one area will spread. So you can see this Amazon fire is intentional, to cut down trees to put in soy and cattle. So we monitor all that. Another vital sign NASA monitors. We also have chlorophyll, precipitation, sea level. There's so much. Soil moisture, here's a pretty cool map. We measure soil moisture and salinity of the ocean with the same mission. So we can actually go and see how dry it is in the Southwest, compare it with the Mississippi, see the soil is 45% moist. And then you can also see the Amazon is in rainy season. And again, you can always go back in time and see the changes. You can also see the Amazon desalinate the ocean. So this is a different unit, a salinity unit. It's saltier here, but where the Amazon lets out, it's less salty. So you can see it desalinate a bit right at the mouth of the river. Same thing with the Mississippi. It's kind of a cool map. You really shouldn't combine two data sets in one, but it's too cool not to. You can see this salt in the mid-Atlantic that actually comes from the Mediterranean. So it comes through the Strait of Gibraltar, and links into the Atlantic. So that's kind of cool. So there's all kinds of maps like these you can explore. And you can just pick them out here on your menu. Water, vapor, nitrous oxide. There's a lot. You can also pick your mission out. So if you have a favorite Earth mission, you can see it here and learn about it. Landsats. And you have events. So here are some of the latest events. Like I'm sure you remember Hurricane Milton, which just happened. So always at the top of Eyes on the Earth is some kind of latest event with some kind of imagery and description. And then you can sort your events by category here, or view them on the globe and go one by one if you so desire. Okay, so that's a quick overview of Eyes on the Earth. There's a lot to do there, a lot to explore, so please have at it. And I've got just a couple more programs to show you. Eyes on Exoplanets. We also track every exoplanet ever found. People seem to like this. So this is a map of every planet that's not in our solar system that we found. So going back into our star, from Earth, we look out and we find foreign worlds. So that's a star. We click on it. Let's see what exoplanets it has. It has one exoplanet that is not in what we call the Goldilocks zone, where it might have life. Let's go look at the planet. So we found this planet. We think it's a Neptune-like giant. You can learn about it here. When it was discovered, what it's like, how big it is, compare it to our sun. If you took the bullet train, how fast would it take to get there? 173 million years, that's no good. A jet doesn't help. Voyager doesn't even help. Even the speed of light is too slow. So even going 671 million miles an hour, it takes 31 years to get here. So we need warp 2 and 3. We can't just go one speed of light. It's too slow. You can actually sort by type. You can go to missions that discover these, like Kepler. Kepler actually stared into space for many years. You bring Kepler up here. Kepler stared in one direction for 2 years because one of its reaction wheels was bad. And look how many exoplanets it found. Every single light there is a system that it found by staring into space. So they're everywhere. We already knew that. We already knew exoplanets are everywhere. But every single one of these is a system. And Kepler found all of them. So right now, if we go home, we can see the total count. 4,000 systems, almost 6,000 planets confirmed, and we find them every day. There's also some hotshot ones that we like to feature, like TRAPPIST. TRAPPIST is only 41 light years away, and we believe it's Earth-like. We believe it has water. And it's got a lot of planets in the Goldilocks zone. It's pretty exciting. And we can compare, actually, let me show you a planet compared to Earth. So every single one, you can do a comparison, just like normal, or Jupiter. Yeah, so that's Eyes on Exoplanets. There's a lot to see there. There's a lot more to do. You can filter by many different things, but this is basically the view. And if you go down to Earth, you can click on View from Earth. You can pick your location. Click on it, and then you can see the view of the exoplanets from wherever you are at night. Now, you will not be able to see this without a very, very, very good telescope. There are some you can, not too many. You can turn on constellations to see where they are. That's your view from your exact lat long, another little feature. That's also in Eyes on the Solar System. Okay, so that is exoplanets. I'm going to show you one or two more things. There's plenty of apps to see. For example, here's a very simple one. Deep Space Now. Who is phoning home? What missions are phoning home and where? We have 3 dish systems: Spain, California, and Australia. In other words, every 8 hours out of 24, you have someone to phone home to. No matter how the Earth is turning, everyone can send their data home. So this is a very simple illustration of that. Our Juno mission at Jupiter is sending right now to Spain. The James Webb Space Telescope is also sending to Spain. Lucy's in California, and Europa Clipper, the brand new mission, is sending data to Canberra, Australia. Very simple. And finally, you can follow the entry, descent, and landing of Perseverance step by step. This is kind of like a little scrolly telling thing. So each and every phase you can see with the 3D on the right and the story on the left. So I'm just going to scroll right through this. Let's get it down to the ground. Heading alignment. Let me just look for a landing site. There it is. Keep scrolling. Straighten up and fly right. And it's going to pop the parachute, which, by the way, is a hidden message talking about JPL. It says "Dare Mighty Things," and it encodes the Latin long, the latitude and longitude of JPL's location here in Pasadena. So that was kind of a secret decoder ring thing. And here it is. Here's the rover with the helicopter on its belly. It's about to drop the heat shield. There it goes. So there's the rover all tucked up inside, ready to land on the ground. Pretty cool. And this was where it was supposed to land. So we did this before it landed, and it actually diverted to go to a safer place. Just a little bit over here, but this is where it was supposed to land. So it finds a solution, it drops the back shell, and it's free flying on Mars. So it has its own rocket-powered descent engine to get it down to the ground, which is really cool. It throttles down, and it lowers it to the ground on cables. We actually have high-definition movies of this looking up and down from each craft. It's incredible. So I would highly recommend finding those on YouTube. And then it drops it and flies away. And here we are, a rover on Mars. Okay, I am going to stop right there and take some questions. So thanks, guys. Why don't you... I'll take some questions now if anybody has it.
Thank you so much, Jason. Yeah, and feel free to put your question in the chat, or you can unmute yourself and ask that way as well.
So for your library, you can set up a touchscreen display. It's evergreen, updated all the time. You can add this visualization to your library website. If you have a theme or some kind of program you have, you can embed it. So it's a free tool for everyone. Please do use it.
Yeah, and I'd love to hear from anyone in the audience if this sparks any ideas about how you might use it in your library programs. We'd love to hear that as well.
Yeah, it's a lot of information, but I would suggest just playing with it, seeing what sparks your interest, and see if you can feature it somehow. And I mean, it works on your phone too. So even just personally, you can just show this off at dinner parties or on long airplane rides.
This is Amelia. When I put this in the chat, on the NASA Eyes page, there's a whole information about how to use it at informal institutions like museums and libraries. But one thing that occurs to me is that so many libraries have kids come in that are doing a report on X, and you can point them to this to really explore. And people can take screen captures, they can record video, they can use it in their own little presentations. It's a great tool for everyone to play with.
Well, I'm always available. Amelia has my email. If anyone has questions, we're happy to help set you up or answer any questions. There's also a feedback link at the bottom of the homepage my team reads every single one of those. So we are available. We're here to help. It's free. You pay for it already with your taxes. Well, you may as well use it.
Yeah, there were lots of oohs and ahs and wows in the chat as you were showcasing the different eyes. I really loved the eyes on asteroids. Made me a little bit scared, a little bit of a thrill, but you were also very reassuring.
Yeah, I'd worry about climate change way more than asteroids.
Yeah,
Way
100%.
more.
You're
Yeah.
totally correct. Absolutely.
Okay, well, I guess I'll turn it back over to you, Claire and Amelia.
Great, so much. We had a comment in the chat. Thank you so much. It's an incredible resource. I never knew we could view this information, and I'll be telling my coworkers about it. It is a phenomenal resource. So many different missions providing their information, and I'm always just so grateful that NASA is open source with their data and putting it in ways that are exciting to explore and learn about. So great. Well, thank you so much, Jason and Amelia, for setting this up. We will be posting this recording on our webinars archive page as well as our YouTube channel. It should be up there in about 1 to 2 days. So feel free to check it out again, pass it on to your colleagues, and reach out if you have any questions. So thank you all so much.
Thanks, guys. I'll send you the recording.